squared. So if you know the initial conditions, we can find C. Okay, so if the initial conditions are given, we can find C. So that's the idea of using the integrating factor method. So you can see that it's not that difficult, but there are certain steps that you need to follow. So here what we did was we multiply by 1 over t squared and we write the form, integrate and multiply again by t squared to isolate y. Good. So next we can talk about what we call the substitution methods. There are 3, so we're going to talk about one by one. So let's talk about the substitution methods. So there are 3 substitution methods, so we're going to do one by one the substitution methods. So we can talk about 3. So let's go with the first one, what we call the direct substitution. Direct substitution. So what's a direct substitution? It will be clear from an example. So what we normally do is let u equal what we call the inside function. Function. So we're going to put the inside function as u, and then we can write the differential equation using the new variable and rewrite the differential equation using the new variable. So let's see this in a problem. So how about this one? Let's say solve dy over dx equal y plus 4x minus 3 to the square, maybe something like that. So y0 equal 4. So let's look at this problem, and you can see that if you look at this differential equation, if you try to expand this one, you're going to get a lot of terms, and it will be very difficult to solve because there are y terms, y squared terms, xy products, and a lot of terms. And you can see that none of the method that we discussed doesn't work for that. So what we can do, we can use this substitution technique. So we can substitute for these inside functions. That's the inside function. So that's the starting point. So what we can do, so the answer, we're going to just the basic substitution. We're going to pick. So let's say let u equal the inside function y plus 4x minus 3. So that's the starting point. We're going to pick that part, inside function. And then just take the derivative. So if you take the derivative, so taking derivative, we can write this one as y prime or dy by dx. So du by dx equal dy by dx on the other side plus 4, because 3 is a constant, negative, so it's going to go away. So that's what you get. And then what you can do is you can solve for dy by dx. So this says that dy by dx equal du by dx minus 4. So we're going to plug in that here. So if you plug in that, what will happen to the differential equation? So dy by dx you can replace by that. So it's going to be du over dx minus 4 equal, we're going to put the inside function as u, so it becomes u squared. So that means, so this says that du over dx is simply u squared plus 4, and you can see that this is a separable equation. This is separable. So we can just use the separation of variable method to continue. So we're going to solve for u first. After you solve for u, then you can use the substitution, to solve for y. Okay, just solve for y. Okay, so that's the idea. So let's finish the argument. So we have so what we have du over dx is equals to u squared plus 4. So we can move the u terms to one side, so we can write this one as du over u squared plus 4. The other side is simply dx. Now what we're going to do, we're going to integrate the two sides. So if you integrate on this side, this is simply going to be tan inverse u, because remember there's a formula. So what the formula says, if you integrate 1 over x squared plus a squared, so this is simply 1 over a tan inverse x over a. So that's the formula says, plus c, and that's what we can use here. So this is one of the formula. It's a direct formula, so we can use that. And also you can find all these formulas in another video. I put all the videos in one formula in one video, so you can see kind of all the common formulas. So you can check the Calc2 YouTube list for that. From that you can find it. Good, and I'll also put a link to in the description, so you can find that in the description of this video. Good. Okay, so that's what you get from the left side. From the right side, it is simply x plus c. That's what you get. So this means that if you take tan of both sides, so this says that u equal tan x plus c, and then what is u? U equal, now we're going to substitute back. Okay, so since u equal y plus 4x minus 3, you can put that here. 4x minus 3 equal tan x plus c. Now you can just solve for y. So you can see it's very simple. So y equal, if in the general solution, is 3 minus 4x plus tan x plus c. So that's the general solution. And if in the initial, if you want to solve the initial value problem, so you can use the initial condition. So the initial condition y0 equal 4 gives, so we plug in that, so the 4 equal 3 minus 0 plus tan c. So this says that tan c equal 1. In other words, c equal pi over 4. That's just one value. There are infinitely many values. So this is one solution. Okay. So one solution, c equal pi over 4. That means you can plug in that, and you can write one solution as 3 minus 4x plus tan x plus pi over 4. If in the general solution, we know that for tan you need to add k pi. So that's going to give you all the possible solutions, because we know that the tan has the period pi, so you're going to add multiples of pi. Okay. Good. So that's the solution. But if you need the complete solution, general solution, like with all the cases, so it's going to be negative 4 pi plus tan. We can do x plus pi over 4 plus k pi, where k is a integer. So that's going to give you all the cases, because the pi is the period of tangent function. Okay, so yeah, so you can see that the basic substitution method works very well, and then you could solve the problem. Okay. So again, so after you solve for u, what you're going to, so this is where you solve for u. So you see solve for u, and then what you do, you use a substitution to solve for y. Good. So that's the what we call the basic substitution method. So let's talk about what we call the next one is the homogeneous equation. So this is the second meaning of the homogeneous equation. Here homogeneous means you can write the differential equation in as a function of y over x. So that's the idea here. So let's look at that now. So this is number 8, homogeneous equations. Homogeneous differential equations. So what is a homogeneous equation? This is one definition of that. A differential equation that can be written as a as dy over dx, a function of y over x. So if you can write the differential equation in this form, we call it is a homogeneous equation. Okay, a differential equation that can be written as dy over dx is called a homogeneous equation. So this is like a one definition. This is like the easy definition. So in this case, what we're gonna do, since you can write the differential equation as a function of y over x, we're gonna pick that. So the solution method is, so we're gonna let v equal y over x. So that is the substitution we're gonna pick, the special substitution. And then after that, we can write this equation as y equal v over x. And then what we can do is we can take the derivative. So once you take the derivative, what's going to happen? This is y prime. Just use the product rule. So you get v plus x v prime just by the product rule. So we're going to use this as well. So we also need that. So those two are always the case with the homogeneous equation, no changes. So we can use that. And then the next step is, after we do that, then you can substitute that, and then you get a differential equation in terms of v and x. So solve for v first. So so we can say rewrite the equation in v and x variables, and then solve for v first, and then use y equal vx. So simply multiply by x to solve for y. So that's the kind of argument. So it's not that difficult. Okay, so so let's look at this in a problem. So as the first example, let's say this one. Solve xy dy over dx equal x squared y squared. Along with y1 equal, let's say, square root 2. So let's try to solve this equation. And you can see that this is not the basic substitution. This is not separable. This is not indicative of factors. So you can use any of those techniques to do this. So what we're gonna do, we're gonna see this term. So we can divide by that term both sides. So that's the starting point. So the answer, dividing by xy, so we have dy over dx, which is x squared plus y squared over xy. So if you divide x squared, okay, let's show the steps. Xy plus y squared over xy. You can see x get cancelled, so you're gonna get the first one become x over y. Y get cancelled, the second one become y over x. Okay, now you can see that this is a function of y over x, because x over y is 1 over y over x. So that means everything looks good, because the first one you can divide by x in the top and bottom. So you can write this one as 1 over y over x plus the other one is y over x. So that is a function of y over x. Now what we can do, we can use a substitution now. So let v equal y over x. Then we know that y prime equal v plus v prime x. So we're going to substitute. So when we substitute, dy over dx means y prime. So this side becomes v plus v prime x. The other side is 1 over v plus y over x is v. You can see, interesting part, this get cancelled. So that term going to go away. So you simply have v prime x equal 1 over v. If you write this using derivative notation, dv over dx, x equal 1 over x, you can see this is a separable equation. So this is separable. So what we can do, we can separate the two variables. So if we separate the two variables, we can write this one as v dv on this side, the other side 1 over x dx. Now we can integrate the two sides. So integrate v with respect to v, so it's get v squared over 2. This one 1 over x means ln x plus c. Just add c to one side. So we solve for v. Now what we can do, we can use substitution. So use y equal vx or v equal y over x. To write, you can write this one as 1/2 y over x whole thing squared. Here this is ln x plus c. Now we can multiply both sides by 2x squared to isolate y. So this says that y squared equal 2x squared ln x plus c. Now what we can do is we can solve for c. So let's say using y1 equal 1, we have actually not 1, y1 equal square root 2. Square root 2, we can substitute, so this square root 2 squared, that's the y value, x value is 1, and then we have ln 1 plus c, but we know that the ln 1 is 0. So this says that 2 equal 2c, says that c equal 1. So we can plug in that value back here. So it is 2x squared ln x plus 1. And now what we can do is we can take the square root. But be careful, when you take the square root, you get plus or minus. Now the question is, which one gonna work? But we know that y1 equal square root 2. That means which is positive. So that means you have to pick the positive root here. So it is 2. So we have yeah. So we have the 2 there. So that means actually c equal 1. Yeah, so let's actually forgot so c equal 1. Now what we can do, we can do the square root. So you only get the positive one, so it is x. So this is 2 ln x plus 2 inside and the square root. So we only pick the positive one since y is greater than 0, y positive, because we know the initial condition says y positive. Because if we had picked the other one, you get negative answer, so that's not going to work. So that means if you are given that, so let's say if you had y1 equal negative square root 2, if this is given, you can see that c is still 1, but you have to pick the negative one in this case, negative solution, because otherwise it does not satisfy the condition, because we know that when you try to solve for y, you get plus or minus. Okay, so this is what I'm talking about. When you have y squared equal, let's say 4, y can be either plus or minus 2. So which one? It depends on the rest of the problem. So that means if you are given an initial condition like y1 equals square root 2, you want to make sure that it satisfies the condition. That means you have to pick the negative one in that case. So here only the positive one works. Okay, I hope you understand the argument there. Okay, now let's go to the third type of substitution. So the third type is what we call the Bernoulli equation. So let's talk about that. So Bernoulli's equations, Bernoulli equation. So what's the Bernoulli equation? So this is the extension of the first order linear differential equation. So it is dy over dx plus pxy. So we still have that part, but the other side is different. It is y to the n power. So that's a yn term. So that's the difference. We have the extra term on the other side, yn. So there are special cases to consider. So if you get this one, this is the Bernoulli differential equation with that y to the n term. But there are some special cases that we need to consider. What if n equals 0? So n can be 0. Then you're going to get dy over dx plus pxy equal qx. So that is our famous one. So this is the integrating factor method. Okay, that's the integrating factor method. So not very interesting. I mean, we know how to do that. Okay, it's interesting, but we know how to do it. If n equal 1, what happens? So dy over dx plus pxy equal qxy. So if you get that, we have two options. One option is we can bring this term to the other side. So if we bring this on to the other side, so there are two ways to do this problem. So one way, we can write the differential equation like this. We can bring that term to the other side, and then what happened? Y is common, so you can see this again first order linear. So this is integrating factors. Integrating factors. Now, if we bring this term to the other side, to the left side, so this can be qx minus px y. You can see this is separable. Okay, so this is separable. So that means we can solve these two cases. N equals 0 case is integrating factor. N equals 1 case, you can solve in two different ways, either integrating factor method or you can use the separation of variable method. So what we are interested in this one is we can consider the case where n not equal to any of those numbers. Okay. So that means if n not equal to 0 or 1, we have a new case, okay, new situation. So that's the Bernoulli equation. So we're gonna talk about that. So let's talk about that a little bit more. So if n not equal to 0 or 1, what we're gonna do? We're gonna divide. So dividing by y to the n, we can divide the equation by y to the n term. Divide by y to the n term. If you divide the equation by y to the n term, you're going to get 1 over y to the n dy over dx. And then here you're going to get px. This can be y 1 minus n, because we can divide by y to the n term. We already have one y term, so it's becoming y to the 1 minus n. On the other side, it becomes just qx. Okay, now we're going to do a special substitution. So the substitution is we're going to substitute for this term. That's how we do. We're going to substitute for that whole term. So let v equal y 1 minus n. So that is the substitution you want to remember. Okay? And that's why n cannot be equal to 1, because if n equal 1, this is just 1. So it's not going to work. That's not a variable, just a constant. So take the derivative is going to be 0. Now what we can do, take the derivative. So taking derivatives, we can write this one as v prime. So we can use a chain rule here. It is 1 minus n, y you subtract one more, so minus n by n y prime by the chain rule. So this is a chain rule. Good. So that means we can solve for y to the n y prime term. So this says that y to the minus n y prime is simply 1 over 1 minus n times v prime. So that's always the case. Now what we can do, we can substitute that in the equation. So if you go back and substitute in this form, so you're going to get 1 over 1 minus n v prime, that's the first term, plus px v equal qx. And you can see this again first order linear in v. So this is first order linear, in v. That means we can use integrating factors. Okay, so use integrating factors. Use integrating factors to solve for v, and then use v equal y to the 1 minus n to find y. So that is the argument. Okay, so that's how you solve the Bernoulli equation. So let's look at one example to see how it works. Good. So how about this one? Solve, let's say 2x dy over dx minus y equal 6x squared y cube. This one. So you can see we have this term, and this is Bernoulli. This is a Bernoulli equation. So we divide by that term. And also you can see that there's an unnecessary term here. What's the term we have here is, and you can see, so dividing by, we also going to divide by x also. Actually you can divide by 2 also, but we can leave 2 and you can see how it works. So dividing by x y cube. So you're going to get 2y cube y negative 3 dy over dx minus 1 over x y negative 2 equal, one of the x terms get cancelled, y3 get cancels, so you're going to get c 6x. That's what you get. Now the substitution. So we divide. Now you can see that you get to the form that we want. Now we're gonna substitute for that. So we're gonna say v equal y negative 2. This implies that v prime equal negative 2 y negative 3 y prime. In other words, y negative 3 y prime is negative 1/2 v prime. I mean, that's what happened, so we read it like that. And now we can substitute that. So if we substitute that, so by substituting substituting 2 times negative 1/2 v prime, substitute for that, and then minus 1/2 v equals 6x. You can see this get cancelled, and then you're going to get negative v prime negative 1 over x v equals 6x. You can multiply by the negative sign, so v prime plus 1 over x v equals 6. You can see this is first order linear in v. That's exactly what we want. First order linear in v. So let's use the integrating factor method. So the integrating factor I equal e to the px dx. So e to the 1 over x dx, e to the ln x, that means x. So we get that. Now what we can do, we can multiply by that both sides. So multiplying by x, so we're going to get x v prime minus plus v equal negative 6x squared. This side is automatically the v and the integrating factor, which was x, equal negative 6x squared. Now integrating. Those steps are just the integrating factor argument. Integrating, we're going to get vx equal, if you integrate this one, it's going to be negative. So you're going to divide by 3, so it's 2x cubed plus c. So that means v equal, if you divide by x, it's negative 2x squared plus c over x. Now what we can do, using v equal y to the negative 2, we're going to substitute that. So we have 1 over y squared, which is y to the negative 2, equal negative 2x squared plus c over x. So what you want to do now is you want to flip it over, but before you flip, you're going to get the common denominator here. You have to do that. So x, so that means you're going to multiply by x, so you can write this in a c minus 2x cubed. Now you're going to flip it over, so that means y squared is x over c minus 2x cubed. Now again, considering cases, you can say y equal, since we don't know, we can write plus or minus x over c minus 2x cubed square root. So those are all the cases, the two cases, and if you know the initial conditions, we can find them. Otherwise, this is the general solution. So this is the general solution. Okay, so that's about that. So that's the basic, that's the substitution method. So we talk about the basic substitution, homogeneous equations, and then the Bernoulli equations. So, and then the last type of first order differential equations, the exact differential equations. So let's talk about that now. So this is the last type we talk about, what we call the exact differential equations. So what we mean by exact differential equation? So we can look at the standard form, which is m a function of xy dx plus n a function of xy dy equals 0. So that is the standard form we're going to consider. Okay, it has to be dx plus dy. But there are other ways to write the same equation. For example, if you divide the equation by dx, you can write this same equation in this form as well. So you can write this one as, for example, dy Yeah, I'm gonna write it down here because I need some space. So we can, by dividing by dx, we can write this one in, for example, dy over dx times nxy plus mxy, just by dividing by dx. But we don't do that because this is really not the right way to do it. We're gonna go with the standard form above. So this is what we call the standard form. We do that for a reason, because there are differential equations we're gonna come, like in physics and mathematical physics, come into this form. So that's why we kind of study that. Now let's talk about the theories that we discussed. So what we call, if the daba m, there's a partial derivative of m with respect to y, equal the partial derivative of n with respect to x. If those two are equal, we call this differential equation a exact equation. Okay, that's the kind of test. The equation is called exact. Is called exact differential equation. This is the kind of test we use. In that case, what happened? There is a function. There's a function f x y equal a constant. So there's a function like that, such that the partial derivative with respect to x equal the m function, and the partial derivative with respect to a y equal the n function. So it says that if that is the case, if this condition satisfies this condition, there is a function such that fxy equal constant, c is a constant, that can give you w f over w x equal m and w f over w y equal n. Okay, and then if you know that function fxy, what we're gonna do, we're gonna solve that function. We're gonna solve for y. So that's what we do, and then that y is the solution we are looking for. So let's look at a problem. Before we do that, actually, let's talk about the solution method. So what we normally do is we're going to start with one of those equations. There are two equations. So we start with the easy one and then take the integral. Once you take the integral, then you get the function back. So that's the kind of idea. So let's try the steps here. So let's call the solution method. So this is the lengthiest argument that we use in differential equation. Yeah, so let's say you can pick just one of them. So let's say you go with the x function, x derivative. So let's say you pick that one. So you can just reverse the same argument. You can just rewrite the argument using the other one if you want. But let's go with this. And then what you're going to do, since this is a partial derivative with respect to x, we're going to integrate with respect to x. So it's very important. So integrate with respect to x. So if you do that, you get the function back. It's a function of xy. It's the integral of mxy with respect to x. Since it's a partial integral, maybe you had a function, only a function of y, because since you are taking the partial derivative with respect to x to find w f over w x, maybe there was a function of y alone. So we just put that back in. So that's a new term. It's not a constant, it's a function of y. Now what we're going to do, you're going to combine the two. So we're going to differentiate this one. So differentiate with respect to y variable. So if you do that, then you're going to get w f over w y. That means you're going to integrate whatever the answer you get with respect to y, because it's a function of x and y. We want to integrate with respect to x. So what will happen here? It just becomes this regular derivative because it's a function of y only. We don't need partial derivatives there. Now what we can do, we can solve for gy. But the goal is to find this. That's the only thing we don't know. So the goal is find. That's the goal. Find this. So now what we can do, we know that this should equals the ny function, because this is the partial derivative with respect to y. This is exactly the nxy function. So we're gonna set it here. We're gonna set that. We're gonna set this equal to this. Now what we're gonna do, solve for g prime y. Okay, or simply solve for g prime y, because we can find it because they match. Then you can find g prime y, and then integrate and find gy. So the next thing is first find g prime y, and then solve for or integrate, and then we can integrate that. First find gy, and or let's write like that. First find gy and integrate. It's a derivative. Integrate to find gy. Now what we can do, we can substitute that in the just the function above. Once you substitute that there, so what we can do, we can substitute substituting we have f xy function. So we can substitute here. We know this part plus now we know gy because we found that above. Okay, now we are not done yet, but we know that the function, what we can do, we can set this equal to a constant, because that's the function we are looking for. We know that there was a function which is fxy which is equal to a constant. So we set that, we put there, and then solve for y if possible. After that, what we can do, solve for y if possible, because sometimes we cannot do that. But if you cannot do it, you get an implicit solution for y. So you get implicit solution for y, because if you cannot solve, it's an implicit solution. So that is the solution method. I know it's a little lengthy, but that's how it works. And then we also talk about a shortcut method. So I'm going to discuss that. So you can use that if you remember. That's not that difficult. It's very easy. So let's talk about the shortcut method. So the shortcut method so what was that? So I'm going to write that you may also use the shortcut method. So what's the shortcut method? We can start with daba f over daba x equal m xy function, and since the partial derivative with respect to x, what we can do, we can integrate this one with respect to x. So integrate with respect to x. Once you do that, you get a function. So what happens when you do that? I need some space here. Once you do that, you get the function fxy. So you get a function. You just integrate with respect to dx. So when you integrate, you can see that you're going to simply consider y is a constant. So you get some expression and do the same thing. So what we do, daba f over daba y, which is n xy. What we can do with this, you can integrate with respect to y. So you again get the same function in another form. So here what we did the partial integral with respect to y. Now what we can do, we can write the common terms once, uncommon terms once. So your function f is simply, you write common terms, and uncommon terms once. So that's the argument. So after you get that, now what we can do as before, we're going to set fxy to a constant, and then after we do that, so we set that. After that, what we can do, solve for y if possible. Okay, so that's a shortcut. So you start with dou by f over dou by x, integrate with respect to x. You go with dou by f over dou by y, integrate with respect to y, and then you get two expressions. You write the common terms once, right? The common terms, you can see some common term once and uncommon term once. That's the function fxy. You say this equals 0, solve for y is possible. So let's look at a problem. So this is, so let's say solve. Three ex minus y squared dx plus 3 minus 2xy plus sin y dy equals 0. So if you get a problem like that, the first thing that we do is we check whether this is exact. So this is the m function. This is the n function. So what we're going to do, we're going to check, we're going to do the test here. So the test is we can do dou by m over dou by y. Remember the m function do with respect to the other one, so dou by y. So which is negative 2y. And you can see that that's exactly equals to dou by n over dou by x. If you respect to x, the constant, the sign term goes away because it's a partial derivative. You get negative 2y. So they are equal. That means it's an exact equation. Okay, that's an exact equation. So that means that means that there is a function. There's a function z f. There's a function z which is simply f x y equals c, such that, so there's a function z which is a function of xy, such that dou by f over dou by x equal the m function, which is 3ex minus y. Now what we can do, we can integrate this back to x. So integrate with respect to x. So if you do that, you get fxy. If you integrate with respect to x, it is 3ex minus actually it's y minus xy squared plus gy, because we don't know whether there is a function. So I'm going to call this equation number 1. Now what we can do, we can differentiate this one, differentiate with respect to the other variable y. So if you do that, you get dou by f over dou by y. So if you differentiate with respect to y, this is 0 minus 2xy, because it's a y, so you get 2y. With minus x, you get minus 2xy, and then plus g prime y, because it's a function of y only, so it's just the regular derivative. Now we're going to set this equal to the nxy function, because we know that by the theory there is a nxy function. We can set it, we can set to that. So it is 3 minus 2xy plus sin y. So it's clearly, you can see that this function has to be 3 plus sin y. When you set them equal, g prime y has to be 3 minus sine y because they are equal to each other. Good. Okay, so we know that. So that means, so this implies that g prime y equals to 3 plus sine y. Now what we can do, we can integrate with respect to y. So integrate with respect to y, and if you do that, you're going to get gy equals to the integral of g prime y dy. That means if you integrate, it's a simple integral with respect to y. So you can see that you're going to get 3y plus, this is sine. So sine means negative cosine y. And we are not adding plus c here. Now by equation 1, since we find y, we can substitute. By equation 1, fxy equal 3ex minus y squared x plus 3y minus cosine y. So that is the gy function. That is gy function. So what we do, we're going to set this equal to c by theory. So there's a constant function fxy that satisfies those conditions. So now what we can see, there's no way you can solve for y. So then the implicit solution is, given by 3ex minus y squared x plus 3y minus cosine y equal constant. So that is the implicit solution for y. And you can see that since we have the cosine y term and the y squared term, there's no way you can solve this for y. But if you do not have cosine y term, then you can solve this for y, because you can use the quadratic formula and then you can solve for y. But since you have the cosine y term, we cannot solve. Good. So this is how we solve an exact differential equation. So next we can talk about what if it is not a exact equation. So what we call the almost exact equation. So we're going to solve that next. So next talk about how to solve almost exact equations. So almost exact. So what's going to happen, if you look at the standard form of the exact equation, mxy dx plus n xy dy equals 0. So what can happen, when you take the partial derivative, the first one with respect to y, it does not equal the partial derivative with of n with respect to x. So that's happened. So in this case, you can see that the equation is not exact. It's not exact. So what we're going to do, we're going to use the integrating factor method. So we're going to use the integrating factor method. So we're going to use integrating factor method. So there are two cases to consider. We have two cases. So so the first one is, we're going to calculate my minus nx over n. We calculate that if this is a function of x only. If this is a function of x only, so let's assume that this is a function of x only. It's a function of x only. In that case, we're going to calculate the integrating factor. Is also going to be a function of x, which is e to the, we can integrate that expression my minus nx over n with respect to x. So that's the integrating factor in that case. The other case is nx minus my over m. So this is a function of y only. If this is a function of y only, then you're going to calculate the integrating factor iy, which is e to the nx minus my over m dy now. So how you can remember them? So you can remember them like this. So you can see this is m n n. The other one is n m m. So that's the format of that, m n n or n m m. Good. And then after you find integrating factor, the rest of the problem is exactly the same as what we normally solve a problem in using integrating factor methods. After that, what we can do, then we're going to multiply by the integrating factor. Then we're going to get I times m dx plus I times n dy. So this is the exact equation. So we're going to follow the exact equation argument. This is an exact equation. So we're going to follow the exact equation argument. So let's do one example just to see how it works. Good. So let's solve this problem. So let's say solve xy dx plus 2x squared plus 3y squared minus 1 dy equals 0. So let's solve that. So what we gonna do, we're gonna pick this as m, we're gonna pick this one as n. Then you can see that dabba m over dabba y, which is x, and dabba n over dabba x, which is 4x, and you can see that they are not equal. So this says that dabba m over dabba y not equal to dabba n over dabba x. So that means not exact. So not exact. So what we're gonna do, we're gonna see which one gonna work. So let's calculate my minus nx over n first. So what do you get? What is my? What is the y derivative with respect to y derivative of m, which is x, and the minus, let's calculate the x derivative of n, which is 4x, divided by n. N means 2x squared plus 3y squared minus 1, which is you can see that this is not only a function of one variable. Okay, so you can see that not a function of one variable. So not a function of one variable. So that means it's not going to work. So let's look at the other one. So nx minus my over m. So if you do that, you're going to get nx, that is 4x, my, that is x, divided by m. Now m is xy. So if you cancel x, so it's going to be 3x over 3 over y. So you can see that this is a function of y only. So the function of y only. So that means we can find the integrating factor. So iy is e to the formula nx minus my over m dy. We already calculated that. So it is 3 over y dy. That means 3 ln y. So bring it here. So that means it's going to be y cube. So y cube is the integrating factor. So we're going to multiply by that. So multiply by y cube, the differential equation. So you're going to get x y to the fourth power dx plus you're going to multiply by y cube. So it is 2x squared y cube plus 3y to the fifth power minus y cube dy equal 0. So that's what you get. And you can see that once you do that, it's going to be exact, because that's how we pick the numbers. So now this time we can use a shortcut. Let's use a shortcut to get the answer. So this is exact. So we use a shortcut method. So we use the shortcut method. Okay, so let's use a shortcut method. So if you use the shortcut method, what do you get? We're gonna go da by f over da by x, which is the first function. So we're gonna integrate this one with respect to x. So if you do that, you get fxy equals to x squared over 2y to the fourth power, because we integrate with respect to x, and we are not going to add the constants. And then go with the other one, da by f over da by y, which is the other function. So it is 2x squared y cube plus 3y to the fifth power minus y cube. We're going to integrate this one with respect to y. If we do that, you get fxy equal 1/2 x squared y4 plus 1/2 y to the sixth minus 1/4 y to the fourth power. Now what we can do, your fxy function is, we're going to first write the common terms, and you can see this is common. So we can write that once. So 1/2 x squared y to the fourth power, and then write the uncommon terms. So 1/2 y to the sixth minus 1/4 y to the fourth. Now what we can do, we set this equal to 0, and you can see that it is not easy to solve this for y. So that means this is the implicit solution. This is the implicit equation, implicit solution, implicit equation for y. So that is how we solve the almost exact equation. And there are, like, cases you cannot really solve because we only consider two cases. Whether my over nx over n is a function of x, or nx minus my over m is a function of y. What if it is not the case? So that means there are some cases that still give you problems. Okay, and then there's a video, what we normally call it all-in-one video. It's already posted. So that's a kind of good one that's going to give you kind of all the methods in one video. So you can look at that. It's in there. I'm gonna also put the link to that video, all-in-one review, all-in-one review for first order equations. Okay, so it's gonna show you all the formulas there. Good. Now what we're gonna do, we're gonna discuss the numerical solutions, and you can see that there are a lot of equations that cannot solve. Okay, there are only few equations, just a very small percentage of equations that you can solve. So that means there's a need to solve, we need to find approximate solutions. To find approximate solutions, we're going to use numerical techniques. So let's talk about that. So that is number 12, numerical methods. Numerical methods. When you talk about numerical methods, there are actually we discussed three of them. One is the easiest one, the most obvious one, what we call the Euler's method. And then we have improved Euler. Improved Euler's method. And then the very good one, what we call the Runge-Kutta method. Runge-Kutta method. So the Runge-Kutta method is like very good. It's going to give you answers like excellent answers for certain problems. So let's talk about the Euler's method. That's the easiest one. Euler's method. So how it works? So what's the geometric argument for that? So let's say you have a curve. So what's gonna happen? You are given a point and the derivative, like the slopes everywhere. So you are given the derivative at each point and a starting point. So that's the only information you have. You can find derivative at any point and also give you the starting point. So the goal is to find an approximation for another point at some point. So that means so this is the actual curve. So what you try to do, you're gonna approximate the value at a certain point. So what we normally do is we're gonna divide this into equal parts and then approximate the value successively. So you're gonna calculate y1, that's y1, and then you calculate y2, and then you calculate y3, like that. So so that's the kind of argument we do. We're gonna approximate one by one. We're gonna look at the tangent line. That's how we do. We're gonna look at the tangent line and then calculate the next one. So actually the first one is not exactly correct. So because when you draw the tangent line, so what happen is, let's extend the tangent line. So this is what you get. So that means your first value is here, right here. That's the first value. So that's the first approximation. So that is y1. Now we can use that value and also use the slope at the point to find the next value. So if you draw the slope at that point, you can see it's going to go like that. So that is y2. Okay? That is y2. So like that, we're going to find that's y2. And then we can draw the slope at that point. So it's going to go right here. That's because they're going to parallel to that. That's the slope. So it's going to give you y3. So that's y3. So that's the approximate value. That's y3. So this is the kind of idea. So you're going to look at the slopes at each point and then use the tangent line to approximate the next point. So that's the kind of idea. So what we normally do is we're going to divide this into equal subintervals, h, like that. And every time calculate the next point. Calculate the next point. So what you are given is simply you are given dy by dx fxy. So that means you know the slope at every point and also you know the starting point. So those are the only things you are given, the slope at every point and the starting point. So and then our formula becomes like this. So your n plus 1 node is simply xn plus the gap, and then your yn plus 1, the next one is simply y current one plus h times xn yn. So that is the scheme for the Euler's method. So this is the Euler's method formula, and this can work. We can start with n equals 0. Once you plug in 0, you get x1, and when you plug in 1, you get x2, 3, like that, depending on how many points you need. Okay, so that's it. So that's the Euler's method. So let's just look at an example and see how it works. So let's look at an example. So let's do this example. Let's say approximate y2 using Euler's method if given the differential equation dy over dx equal, let's say, 3y minus x and y0 equal -1, and the step size 0.5. So this is a kind of problem that you can get. You get a differential equation, initial condition, and a h. So it is always a good idea to kind of try to understand what's going on here. So we have x0, that is starting value, that is 0, and then we have y0, that is the y value. So how many we need to calculate? So you can see that x0 is 0, and then we're gonna go in 0.5 steps. So that means we have 0.5, and then 1, 1.5, and 2. So you calculate at 2. So that means x1, x2, x3, and x4. So knowing x0 and y0, you want to calculate y1, y2, y3, and y4. You calculate 4 more. So let's look at the situation here. So what we have is, so the answer. So what we can do, we're gonna first identify what is the x y function. So you can see it is 3y minus x. That's the xy function. Now we got the scheme. So what's the scheme? Xn plus 1 is xn plus h. So in this case, it is xn plus 0.5. So every time you increase by 0.5. And then yn plus 1, which is yn plus h, f xn yn. So let's plug in and simplify. So this is yn plus h is 0.5. The function is 3yn minus xn. So you plug into the function, because that's a function. So you plug in for that. Now what we can do is we can simplify. If you simplify this, what do you get? You're going to get 0.5 times 3 means 1.5 plus 1. So it is 2.5 yn minus 0.5 xn. So that is the formula that we're going to use for each n. So we can start with, we have x0, which is 0, and we have y0, which is -1. Now we can start plugging the value. First value is 0. So when you plug in 0, you get x1. So when you plug in 0, you get x1, which is, you add 0.5, so it is 0.5. And y1, the formula says it is 2.5 y0 minus 0.5 x0. Since you know the two values, we can plug in. So it is 2.5. y0 is -1, and then y0 is -1, and then we have 0.5 times x0 is 0. So if you simplify, so you can use a calculator for that, you're gonna get -2.5. So that is the y1 value. So keep doing. So now you plug in n equal 1. If you plug in n equal 1, you get x2, which is 1.0. We have y2 now. So it is 2.5 y1 minus 0.5 x1. since we know y1 and x1, we can plug, that's coming from the previous step. It's always those two coming from the previous step. So we're going to plug in those two. So you're going to get 2.5 y1 means negative 2.5 minus 0.5 x1 means 0.5. Always coming from the previous step. So if you use a calculator, you're going to get negative 6.5. Go to the next one. N equal 2. So this is going to give you x3, which is 1.5. This is going to give you y3 value. According to the formula, it is 2.5 y2 minus 0.5 x2. We know all the values from the previous step, so it is 2.5 negative 6.5 minus 0.5 and then x2 is 1.0. Now what we can do, we're going to simplify again. So you're going to get negative 16.75 is a calculator. And then we can find n equal 3. You get x4. That means that's exactly the number we want. y4, that's the value we are looking for. Again, it's the same formula. It is 2.5 y3, we know that. And then 0.5 x3, we also know that. So let's plug in there. So you get 2.5 negative 16.75 minus 0.5 and then 1.5. So if you use a calculator, you're gonna get negative 42.625. But this method is not very accurate, so you don't need this many decimal point. We normally leave like just one decimal point. So that means your y2 value, which is the y4th, y2 value means the y4th, is approximately equal to negative 42.6. Okay, so you can see it's not that difficult. So it is always a good idea to get this first, because then you can simply plug in there every time rather than using the original equation every time. So always try to simplify that first and then use that simple equation. This is much easier. Okay, so so this is how you use the Euler's method to find the approximate solution. So next what we're going to do is we're going to discuss the most correct version, what we call the Runge-Kutta method. So this is very accurate. Even the commercial softwares use that. So I should say that. So this is excellent result. Like a very similar problem. So you have y prime equal fxy. So the slopes are given with a initial condition y x naught equal y naught. So you have a so you know the starting point and you also know the slope. So then the goal is to approximate the actual curve. The same idea. We're gonna split as before, though we're gonna call the gap is h and into find the value at xn. So so the scheme is slightly different now. So what we're gonna do, we're gonna calculate several intermediate values. So we're gonna go for n equals 0, 1, 2, like that, depending on how many you need. As before, we're going to calculate the x naught, which is xn plus 1 equal xn plus h, no change. But before we calculate y, we're going to calculate several other slopes. So we're going to calculate k1 slope, that is the slope at xn yn. Then we're going to calculate k2 slope, that is the slope halfway in between. So you're going to go xn, you go h over 2, comma, yn plus h over 2 times k1, and then k3 slope, which is f again at the halfway point, comma, yn plus h over 2k2 now. So we have k1 goes there, and then k2 goes there, and then we have k4. So what is k4? Which is f xn plus h yn plus h times k3. So we're going to calculate those extra slopes, and after you calculate the slopes, then your yn plus 1, the next approximation value is given by yn plus h divided by 6 times k1 plus 2k2 plus 2k3 plus k4. So that is the Runge-Kuttai scheme. Is very similar. You know x0, y0, so you can calculate x1, y1, x2, y2, x3, y3, like that. So this is what we normally call the fourth order Runge-Kuttai. Fourth order Runge-Kuttai method. So normally called RK method. Runge-Kuttai method. This normally used in what we call OD45 algorithm in MATLAB and other softwares. Use an improved version. Use an improved version of this. Okay, so that means it's very accurate. The solutions are very accurate, and we solve several problems in the homework. And you can look at that. Also, we have solved several problems in the video as well. So if you need more information, you can find them. Good. So this is the Runge-Kuttai method, and I'm not going to solve a problem from this one because it's very lengthy. Because you know that there are many things you need to calculate before we calculate the next one. Okay, so this is how we gonna solve a. This is the next good numerical method to solve a first order differential equation. So next, let's talk about what we call the directional fields. Directional fields. Some also call this slope field. Slope field. So what's the directional field? So what we're gonna do? So when we have a differential equation, so let's say you are given a differential equation dy over dx equal fxy. So what we can do is at each point in the domain, draw an arrow indicating the direction of the tangent line, indicating the direction of the tangent line, the direction of the tangent line. So that's what we call the directional field, or the slope. The direction of the tangent line means the slope. So we can do look at a problem. So let's say draw the directional field of let's say dy over dx equal 2x minus y. So if you get a problem like that, what we're gonna do, we're gonna draw like a typical grid, with enough points. So let's do that. So this is a grid. with enough number of points. So normally like this will be given. So let's divide this into three parts. Um, so what we're gonna do, let's say this is 0, and then 1, 2, 3, and then -1, -2, -3, like that. So this is 1, 2, and then -1, -2. So what we do is, um, so this is the x direction, and this is the y direction. So we're gonna at each point you can evaluate the slope and draw a small line. And we know if there's a positive slope, so the arrow goes like that. This is for positive slopes. If you have a negative slopes, that's the arrow goes down. It's a zero slope, is horizontal. So we can use those three facts. So let's evaluate at 0. So at 0, you can see that if you plug in 0 to the differential equation, you get dy over dx is 0. So that means at 0, slope is 0, so you draw a line like that, the 0 slope. And then also you notice that there's a special line. For example, if you look at this line, so you can say the line, on the line, if you set this equal to 0, so you're gonna get y equal 2x. On the line y equal 2x, the slope is 0. The slope is 0. Slope is 0. So that means, what is this line? So that means at x equal 1, y equal 2. So that means this is the line. So the line passing through these points. So on this line, the slope is 0. So that means if you pick any point on that line, you know that the slope has to be 0. So that's one thing. So we know that on that line, slope is 0. And also let's calculate few other values. So for example, at this point, if you look at this point, you can see that it is x equal 1, y equals 0. So the slope is 2. So it's a line with slope 2. And at that point, you can see slope is 4. So it's more steeper. And here slope is 6. So it's much more steeper, like that. And if you go to the other side, you can see at -1, slope is -2, and -4, and -6. So it's much more steeper. And then if you go along the y-axis, you can see that x coordinate is 0, y coordinates increases, but with the negative sign, it's going down. So for example, at this point, the slope is -1. So it's going to go like that. The slope is -1. And if you go up, it's -2. So it's much more steeper. And here, at -1, it is 1, and this is a 2. And we can also draw a few more. So for example, if you add 1, 1, so you're going to get slope 2 minus 1, so it's 1. So slope is exactly 1 here. And then if you go further, it's the same y coordinate, but x coordinate increases, so you're going to get more steeper, like that. Um, and then here what happened, x is -1, that means -2, and then y is 1. So at this point, what's going to happen is, let's calculate what you get. So you can see the x equal -1, that means it's -2, and 1 is -3, so it's -3. And when you go up, it gets more steeper because y is you subtract y, that means it gets more steeper. And at -2, it's going to be -4, and so it gets more steeper. You go the same thing, when you go this way, it's going to get much more steeper. And what about this point? So this point, you can see x is 1, so it's 2, and then minus 1, so it's 3 because y is negative, so it's 3, so it's more steeper. The same thing, much more steeper when you go that way. uh, so go down, that means it's gonna get more steeper like that. So we only left these, so let's calculate what happened at this point, so which is -1, that means -2, and then we have y equal -1. With the negative, it become positive, so it become -1. And then when you go, it's gonna get much more negative like that. So those are a few values. Okay, so we still have just a few more. Uh, so at this point, what's gonna happen is it is -2, that means -4, and with -2 it's become. So what happened here? So you can see when you go down, you subtract negative values. That means it's gonna get less steeper. So like that. Uh, yeah, because the negative sign, so it's get less steeper when you go down. So that means this has to be less steeper than that. Good. So when you go down, it's get less steeper because the negative y sign. Okay, so that's the directional field for this one, and good. So now what we can do is we can draw a typical curve. Like for example, if you want to draw a curve that passes through one -1, 1, so that means the point, this point, that's the -1, 1 point. So what's gonna happen? It's gonna follow the arrows. So if you follow the arrows, what's gonna happen? It's gonna go like that, go like this, and I think it's gonna go like that, and get 0, and then